Hi, this is Alex from devstories.eu, Python, Cheminformatics, and AI, episode 4 of 22. You would not try to parse thousands of text logs without using regular expressions. Similarly, you should not try to filter chemical databases without smarts patterns. Finding specific functional groups across large datasets requires dedicated structural logic, and that is exactly what substructure searching provides. Suppose you have a library of drug candidates. Your goal is to flag and isolate any molecule that contains a specific known toxic functional group. First, you define that toxic group using a smarts string. Smarts is an extension of smiles designed specifically for querying molecular patterns, allowing you to specify wildcards, specific bond types, or ring structures. You pass this text string into the RDKit function that creates a molecule from smarts. This generates your query object. Your target molecules, the drug candidates, are already standard RDKit molecule objects. To filter the library, you take a candidate molecule and call the method named hasSubstructureMatch. You pass your query object into this method. It evaluates the candidate molecule against the pattern and returns a simple Boolean value. True means the toxic group exists somewhere inside the candidate. False means it is clean. Because this method stops searching the moment it finds a single valid match, it is highly optimized. You can loop this Boolean check across your entire library to quickly split a massive dataset into safe and flagged subsets. Now, what if simply knowing the toxic group is present isn't enough? Perhaps the toxicity scales with the number of times the group appears, or you need to isolate the exact location of the toxic atoms for a structural biologist. For this, you use the method named getSubstructureMatches, plural. You call this on your candidate molecule, again passing in the query object. Instead of a Boolean, this method forces the search engine to map every possible occurrence of the pattern. It returns a tuple containing other tuples. Each inner tuple represents one complete match of your pattern. The integers inside these tuples are the exact atom indices within the candidate molecule. Here is the key insight. The order of those indices perfectly mirrors the order of the atoms defined in your original smart string. This means you always know exactly which atom in the target corresponds to which part of your query. If the toxic group appears 3 times in the candidate, you get 3 inner tuples. You can count the tuples to find the frequency of the pattern, or pass those specific atom indices into a drawing function to visually highlight the toxic regions. If you only need the atom indices of the very first match it finds, you can use the singular getSubstructureMatch method to save processing time. You must also account for stereochemistry. By default, RDKit substructure matching ignores chirality completely. A wedge bond and a dash bond will both trigger a match for a basic smarts query. If your target toxicity only occurs with a specific stereoisomer, this default behavior will generate false positives in your drug screen. To fix this, you pass an argument called useChirality and set it to true when calling any of the matching methods. RDKit will then enforce stereochemical rules based on the specific configuration defined in your query. The true power of substructure searching is that it maps a purely logical text query directly onto the physical topology of your dataset, bridging the gap between abstract string patterns and concrete atomic coordinates. That is all for this one. Thanks for listening and keep building.